Hey there, Unit 3, Lesson 4, coming at ya. So in Lesson 3, I want to take us back to there because we're going to not only just have unit fractions for exponents, like 1/3, 2/3, 3/3, 4/3. Now we're going to be looking at any fraction that we have. So last lesson, we learned that any base to a fractional exponent could be rewritten in radical form, turning that denominator into the number of the radical, the number of the root that we're looking for. So if it was to the 1/3 power, we'd be finding the third root of b, the cube root of b. And we said that this is our exponential form. And we call this thing here, because that's a radical, we call this thing radical form. Now it's important to know that kind of stuff because that is the language of some of our questions. They're going to ask us to rewrite something using radicals or to change it from radical form to exponential form. Okay. So first of all, we have a math talk, just thinking about how we can regroup fractions. It asks you to do this mentally, so again, no calculator. I'm going to do all this thinking out loud from my head. And maybe you're doing that thinking too. Feel free to hit pause here and reason through your own way how you could solve these mentally. It's important that we think how equations go, how multiplication goes. There we go. That we can think of these in different kind of groupings. Finding half of 5, 2.5 is easy, but then 2.5 times 4, not quite so easy. So I would do this one where I do the 5 times 4 first, because it's much easier to find half of 20, which is very quickly equal to 10. And I can see the same thing going on here, this 5/2. Well, again, I am not going to try to do 5 divided by 2. I'm going to think of this like half of 5. I actually rethink of it like this. I would break it back apart. You may think of it as 5/2 times 4/1. And then you may remember that if we are multiplying fractions, we just multiply straight across. Multiply the numerators. 5 times 4 is 20. 2 times 1 is 2. And 20 divided by 2 also equals 10. I would think of the next one in this same kind of way. If I were multiplying fractions straight across, I notice I am multiplying by 2 and then dividing by 2. And I am also dividing by 3 and multiplying by 3. So this one very quickly just turns into 7. So maybe you're also thinking of it using this multiplying straight across thing as 2 times 7 times 3 over 3 times 1 times 2. And that's how we can start to cancel some of those things off in the numerators and denominators. And our last one, I would do the exact same kind of thing. I see I'm multiplying by 7 and dividing by 7. I see I'm multiplying by 3 and dividing by 3. My answer will just turn out to be a 5. So by regrouping and moving things around, we can start to see some cancellations happening. Hopefully that is making some sense to you and a chance for you to see some of that in action before we start doing some of this in action. Because we have another kind of idea here in 4.2. The idea of taking 5 to the 1/3 power and then raising that to the squared, squaring that, Using our exponent rules on page 8 tell us that if we are taking an exponent raised to an exponent, that we could multiply those two together. We multiply these two things, those two exponents. So I could rewrite this like 5 to the 1/3 times 2, which is the same as 5 to the 2/3 power, which is also the same as this idea here. If I have the squared first inside of parentheses, I'm still going to multiply those two exponents together. I would still have 5 to the 2 times 1/3, which is the same as 5 to the 2/3, which is the same as this. So we can use exponent rules to explain why they're equal to each other. It's because it doesn't matter which order I do these in. This is important because I don't know the third root of 5. I don't know 5 to the 1/3 power. So I can't even begin to square it without having a calculator to do this. Here, though, if I have 5 squared, and then I raise that to the 1/3 power, well, I can do 5 squared. I know what that is. That's 25. And now if I want that to the 1/3 power, I can pretty easily, thanks to my information in lesson 2, I can at least estimate what that number is going to be. I'm going to flip back to that page real quick and think 25, because that's what I'm taking the cube root of, is between 8 and 27. It's really close to 27, so this number is going to be very close to 3, but a little bit less. So I would guess that it's probably about 2.9-ish. So if I were given this problem, I would want to know that I can rewrite it in this way, because this gives me a starting point that I can at least work with in my brain. Now, to write these using radicals, I kind of already did that over here. I started that idea at least. It's the same rule that we had up above here. Whatever is the denominator of the fraction would come out and be in front of a radical. It'd be the root that we're looking for. So, to write 5 to the 2/3 using radicals, I would swing that denominator in front and say it was 5 squared, the third root of 5 squared. Or, I could write that it is the cube root of 5 squared, because these two things mean the same. I can square it first and then take the cube root of it. That would look like this, or this. Or I can cube root it first and then square it. So 5 to the 4/3 using radicals. Again, I'm going to use that same idea that I could write it as 5, the third root of 5 raised to the 4th power, or the third root of 5 to the 4th power. These two mean the same thing. 5 to the 4th power is, let's see, 5 times 5 is 25, times another 5 is 125, times another 5 is 625. I could do that if I had more time. Yeah, but 625. So I could also write that as the cube root of 625. Let's add this kind of rule to our rule page on page 8. I told you we're going to keep on adding some rules here, so I want to make sure that we keep on doing that. So in lesson 3, we added this rule here. I'm going to have another one that also kind of builds on this idea, that any base to a fractional exponent like n over m We can write that in one of two ways. We can write that as the mth root of the base raised to the nth power, but it also can equal mth root of b to the nth power all underneath the radical. So these ones are all equal to each other. I can either do the root first and then bring it to an exponent. This is great if I can find the square root or the cube root and it's an even number, and then bring it to a bigger number like an exponent. Or if I can simplify using an exponent first and then find a root. And these work in the opposite direction too. If I'm given something like this, I can rewrite it as a fractional exponent, and that might help me do something like bring it to another exponent, or multiply it, or divide it, or do other things like that. So, we have another rule that we're adding to our toolbox. I might even add that right up here, since this is what we just learned in here, that we can now use any fraction that we want to. The denominator becomes the root. The numerator stays an exponent. Okay, because we can think of that like b to the n to the 1 over m. So that n would still become an exponent, would still stay as an exponent. Alrighty, 4.3, man, they didn't give us a whole lot of space. This is a pretty short lesson, I like that. 4.3 asks us to complete the table as much as we can without using a calculator. It tells us there's probably only 3 places that we can fill in. So if we're bringing 2 to the x power, we know 2 to the 0 power. Anything to the 0 power is 1. I can estimate 2 to the 1/3 power, but it asked me to fill in without using a calculator, and I only need 3 spaces. So I need this 2 to the 1st power. Anything to the 1st power is itself, so that has to be 2. And 2 squared has to be 4. So those are the 3 spaces I can fill in without needing a calculator. To fill in the rest of those, it asks us to plot the points that we filled in. Well, it was 2 to the x, and these were our exponents. And anything to the 0 power was 1. 2 to the 1st power was 2. 2 squared was 4. Connect the points as smoothly as we can. It's going to be a curve, kind of something like that. And then use this graph to estimate some of our other values that we might have. So 2 to the 1/3 power. If I'm estimating off this graph, let's see, 2, 4, 6, 8. No, those are by quarters. Okay, so it's not quite 1.25, but it's really, really close to that. Maybe 1.24-ish. So I'm just adding that to the other side here, this 1.24 idea. To the 2/3 is going to be up here. That looks like just over. Oops, sorry. I just did that over there. That looks like just over half, so maybe 1.6-ish. I don't really know.